All right.
Come on,
I think we're live. All right. So I wish the whiteboard was a little higher, so I'm gonna have to. Actually, I can sit down. It's pretty. It would actually be pretty comfortable. All right. So I'd like to start off the tutorial by going over that one midterm exam question that everyone screwed up. It wasn't your fault. The wording was very poor on the question. The question one, question like the very first question, section one, section three. Yes, that's the one. All right. So the question asks you a particle in the box. Okay, and then you have I forgot what the name is. Partition here that like keeps your wave function here. So this is psi of x root 2 over a right here. Or I can't remember, but it's a constant, all right? And then at some point, let's say time equals 0, you decide, okay, I'm gonna remove this partition here. And then just let it be free, all right? And then the question asks you, what will happen later in time? So basically, you've just expanded the box by 2. And one common answer I got is nothing will happen because this is not time dependent. Well, the real answer is that, so you know how the particle in the box has eigenstates, it has to stick to one of those eigenstates, otherwise it can't like live on forever. Well, then what you actually have to do here is think that, oh, since it's not an eigenstate, it will gain time dependence. I'm not sure if Pat went over this, that if, like, for example, you have a particle in the box and you have state that's not like an eigenstate, not a stationary state, it'll gain time dependence. Like it'll gain a time dependent phase and like evolve in time. So basically, what will happen is that it'll become this will like either become this or this or like one of like the many eigenstates. All right, and then the second part of the question was basically asking, okay, what's the probability of becoming the ground state of the particle in the box? The first excited state, or yeah, like it can become the second excited state, but it's only asking for the first two, n equals 1 or 2. So basically what you have to do, I'm not going to do the math because the math is pretty easy. The hard part was just setting up the problem. What you had to do is just compute the overlap. So basically you have like your bound here, which is from 0 to a over 2. Wait, hold up. Let me look. Wait, this. Yeah, there's a trick to this. I'm glad you mentioned that.
Sorry. So the reason why it will not retain its initial state is because it must achieve an eigenstate.
Yeah, it has to settle to a stationary state.
I have a question about I don't really understand like the notation where it's like it equals root 2 over a.
Yeah, just give me a moment. I'll answer that. Because yeah, I tried doing this midterm on my own, and this question, I misinterpreted the question first. Like I fell into the trap that you all fell into. So I don't think the question was unfair solely because it was poorly worded. So yeah, so this is basically just root 2 over a. So it's like just some constant. Like it's just a straight line at first, but then it has to settle into an eigenstate. And then So the box at first is centered at 0, but then the question gives you like a series of like eigenstates, theta for Bn of x is equal to root 2 over a, like something like some sine functions. Okay, if you have a particle in the box centered at 0, which is what the problem like gives you, that won't work. The eigenfunctions are sine functions and cosine functions. So what you actually have to do is shift your box by a over 2 to have it have one end at 0 and the other end at a. So if you want to compute the overlap, your bounds of integration will be from 0 to a over 2, because you have your psi of x here over like the 0 to a over 2 interval. So this is 2. So to actually compute the overlap, 0 a over 2. So you'd have psi x yes. Well, one of them are starred because of the mod squared, but it doesn't matter since they're both real valued. And if you actually go through the math, so you can actually keep, so there's two ways of doing it, either like substituting the n in and getting like, for example, doing this integral for the ground state function and then the first excited state function, or you can just keep the n in and sub in the n later. But the answer you get, so the probability for getting the ground state and the probability to get the first excited state, so n equals 2, they're both 4 over pi squared, which is about like a 40% chance for each. So you get an 80% chance of landing either, like a total 80% chance of getting the n equals 1 or n equals 2. Yes.
Explain why it doesn't have anything to do with the Hamiltonian inclusive energy.
Okay. So if you're gonna use a Hamiltonian, you want it to calculate an energy. The question doesn't ask you to compute an energy, it asks you to compute a probability.
Of energy?
Of measuring, a specific state. Yeah, I understand see, the wording was confusing. The question, if you read the question, it doesn't ask you to measure, it doesn't ask you for an energy. It asks you to calculate a probability of measuring a specific energy that is like a specific eigenstate.
Energy measurement yields the ground state energy and the first excited state energy.
Yeah, I gotta say the wording on that is really bad. But it's because if you're calculating, so if you're gonna actually like compute like, I'm not even sure the camera can see this. Hold on. Yeah, I will. Okay. So if you're calculating this, yeah, sorry about this. I didn't think this through. All right. So if you're operating with your Hamiltonian to get this, you'll basically just get an energy value, which is not what you want. You want a probability.
So if they said the probability of them being in a place is the same thing as the energy
Like,
measurement yielding the
yeah,
energy.
they're kind of synonymous. Yeah, if it were up to me, I would have like reworded the question. Because I thought like, yeah, it is a difficult question, but if it was worded better, a lot more people would have gotten it right. Yeah.
So, how do you know, how would you have known what to put under the, like, because like, so like we never learned that like in my eyes, like the probability like overlap integral is like the
Yeah, just like your first is basically just the overlap between your two functions. So basically you You just multiply them and then integrate over the bounds.
Okay.
So,
All right, but what was your
Cause like typically when we were looking at probabilities and like overlap integrals, it was like the complex conjugate of the function that we-
itself?
of itself. But
Yeah.
because when I was doing this, I was like, oh well, there is no complex conjugate, and like I can't do any
So
on it.
you're telling me that Pat never showed you that, oh, like, well, this is like stuff that you'll learn in 355, like where you want to compute like like an example of this is, okay, what if you want to compute like the probability of like an electronic transition? So you'll have a ground state wave function and an excited state wave function, and the way you would do that is literally compute the overlap between the two. So you do like, let's say this is your ground state and this is your excited state. So you literally like compute the overlap and you get a number. The bigger the number, the higher the probability. But then Pat only showed you how how to like do it with the same functions. Oh, hi. Hi.
We
Welcome.
can't leave this door open, I think.
Yeah, I
It doesn't
think
stay open.
yeah.
That's not gonna hold up.
Yeah.
Carry on.
All right.
so I don't understand the notation. There's the phi and the other one. Like I don't understand.
Like this.
Literally, like when it says like phi x equals 2 over a,
Yeah.
I do not understand what that means. Because
Hmm.
we've only ever seen like I feel like we've seen like the root over a and then it has like a sign after it, but this doesn't have.
Okay, so basically the problem can I have your copy real quick? Yeah, it's easier doing it. Oh, thank you. All right, so right over here. So it's basically this is basically just a function. It's not an eigenstate, it's just a function. And if you look at root 2 over a, if you go in Desmos and plot this, it's just a constant. So you were wondering, I still don't quite understand which part you're having trouble with. Like, I don't know,
I don't understand like why, because like you're saying we have to add in the basis function and I don't understand why. I don't understand how they relate to each other.
okay, are you basis function?
Like is that not what the other one is? Or is it like a secondary? I don't understand.
I
Like it's
sorry, I don't
like
quite follow.
I'm looking at this and I don't understand like
Okay. Ignore this part for now, all right? So you start out like at time equals 0, you have like you have a snapshot, you start with like a snapshot of your like half-sized blocks, all right? And then the problem literally tells you like an arbitrary, like this is not like an eigenstate, it's literally just like an arbitrary function. You start with that
is that
at the very beginning. Like you have a snapshot of time equals 0, and that's what your like wave function looks like.
so E is like
Yeah, A is the width of the box. So it's literally just a constant over like a straight line. There's no like there's no like sine or trig function. It's just a straight line.
so how is it moving? Like if it's not a function.
Okay.
How is it moving?
All right, I'll get to that.
Okay.
So the box then expands, right? So it increases in size, like effectively, like the problem says, like, oh, it's localized, but it's as if, like, after time equals 0, you decide to expand the box, pretty much, because the problem said it was localized before, so it's as if it was being constrained in a half-size box, and then after time equals 0, you instantaneously expand the box.
How do we know they're not like it will not stay localized?
I'll get to that. So I'm getting to it. So so now you have like just a regular particle in the box, right? So that if you want a wave function to last for any appreciable amount of time, it has to be an eigenfunction, right? It has to be an eigenstate or a stationary state, as you would call it, right? But then you have like just some random arbitrary wave function that doesn't obey like the the boundary conditions. It doesn't. It's not like it's just a weird function. So you have to think to yourself somehow it has to become an eigenstate for it to exist over like a period of time. So what actually happens is that it gains time dependence. It will gain a time dependent phase, and it'll like eventually like I'm sure there's like animations on YouTube or something of the wave function literally like spreading out and then like settling to an eigenstate.
Okay, but just know what makes it strange. Like what makes this function weird that we have to think of it as making it an eigenfunction.
Okay, the reason why the function is weird. Okay, I don't want to like I have to think carefully how to like answer this question, but the reason why it's weird is because once you expand the box, you literally have it just occupy like this part. Like you know how you need to have like a boundary condition for your eigenfunction, right? Well, then you have like you don't have I don't know how to can't remember which boundary condition it is, but you know how every like eigenstate has like a probability over the entire box, and then it goes to zero as you hit one of the boundaries. But here it just goes constant, and then there's just nothing. So it's just, and furthermore, it's like not like I'm repeating myself, and I know it's not helpful, but it's not an eigenstate.
But okay, I've thought additionally.
Yeah.
So I just don't understand like why the function couldn't continue being root 2 over a. Like it's just like over the whole block. Because would it not like I don't understand what changes because you've just doubled the space.
Yeah, you doubled the space, but also if you just kept the box like fixed like that, it'll turn into one of like the trig functions, but instead it'll be like it'll be like confined within there because it's not an eigenstate. The particle in the box, like the boundary conditions of the box, only allows certain like states to like persist like indefinitely.
So
And like this straight line is not one of them.
So are you saying that even if we didn't open up the box, it would still have to become an eigenstate of the little half block?
Exactly.
Okay.
Yeah.
Is 0 not an eigenstate though? Because if the eigenvalue is 0, is that not allowed?
No, that's not allowed. It has to settle to like one of the. Can I see? Okay. Can you restate your question?
Like when it says the wave function in half the box is 0,
Yeah.
is that not an eigenstate for that half of the box?
No, it's an unphysical. It's like I don't know how to describe it. Basically, the wave function that you start with the root 2 over a is like an arbitrary. It's like an arbitrary state. Like it's out of equilibrium. Sort of. It's kind of like a poor analogy, but think of it as something as out of equilibrium and it has to fall back into equilibrium, the equilibrium being an eigenstate. So you start out the problem with something like out of equilibrium. Like I don't know what happened to our particle for it to be like that, but it had to like be perturbed somehow just to be in there. And then you start the problem looking at it instantaneously for that moment. And then after that time, you expand the box, and then it has to settle to an eigenstate of the particle in the box.
So the probability measurements, the probability of which eigenstate is going to settle into.
Yes,
So
that's
the problem is
exactly
going to
it.
settle into the first one or the second.
Yeah. Like we
Okay,
know
so-
for a fact. Yeah, we know. Yeah, and the reason, well, an intuitive, like sort of explanation as to why it like can settle either to like the first or n equals 1 or n equals 2 is that it was like confined particle half size, like is confined to like a half size box that has like a lot more energy than a larger box. So with all that excess energy, it can go like into excited states. At least that's like hand wavy sort of way to think about it.
Okay, so when you're doing this size star side kind of probability, is that the probability of like an energy eigenstate or a position eigenstate? Because when we
I
were
can go
looking
through
at
that.
and here ask for the energy.
Okay. I think Pat didn't really cover. Okay, I have a confession to make. This problem was in our advanced quantum mechanics midterm when I took it last year with him, okay? And on top of that, it's poorly worded. So, I mean, it was definitely a challenge. Don't get me wrong, there was one person in the class who got it right correctly, but everyone, yeah.
Like, and also, how does it gain like an amplitude all of a sudden if it was 0?
It gains a time dependence because it's not a stationary state. Like it can't, if it's not an eigenstate, it can't stay that way forever.
Okay.
Like like when you learn like the quantization,
Yeah.
like before in classical mechanics, any sort of energy state or any like sort of physical state of the system was like pretty much allowed, right?
Yeah.
Like if it was like a tennis ball in like a room, like in a room, like it could have like any function it would want. But since you're in a quantum system with boundary conditions and you're at a small scale, so the wave nature like has like a huge component, it only has like a very like discrete allowed states. And if it's like that, it'll have to like evolve in time.
But I mean, like, why wouldn't it settle into an eigenstate only in the first half of the block?
Because you don't have a confining potential holding it into the first half.
Okay.
Yeah. Yes.
I'm just confused as to why we're squaring. Like in the answer, it says that you square the overlapping equal. Like I guess the overlapping equal makes sense. It's like you're finding because then when we found the probability of
Wait, hold
position
up.
in
Yeah.
class, we didn't square it. The probability for position was just the overlap integral of like the wave function and like the complex wave function.
Okay.
But then in here, when he's calculating probability for energy, he's squaring the overlap integral.
Okay, so you're talking about the last question.
No,
of
I'm talking
the
about
exam.
the first question.
No, but you're drawing like here in this question. Here, you have to do you have to do this, right?
No, but in answer key
He's squared.
here, he's putting it in
If
absolute
it's
value
absolute
and
value
squaring the
You have to square
entire
it.
thing. Like,
I can't remember.
Like
That is-
this has never been seen in class ever. This is not in the textbook. Like,
Oh man.
this is
Like, that is the
nowhere.
energy thing. Like, we only did probability for
It's just like so.
Do you think this is not related to this question specifically, but can you tell Pat that you're not following what's happening in class?
Like,
Because I can't find, I think that's like hours thinking about how I could tell him, and the closest thing we got so far is to write him a fucking letter.
Okay, this is stressing me out too. Right. Okay.
But genuinely, no one understands what's happening in
every single
class.
chapter been so far, and I've never found this.
Yeah, I've also read the entire chapter, like all the chapters.
Yeah. My question.
Don't know what else
Basically,
to do.
let me
make
say
it
this again.
better.
This was in our advanced quantum midterm, which uses a different textbook, which is probably more in line with the material that's in that textbook.
He said he pulls some of the stuff from Levine.
Okay. I've never laid eyes on that book. All right. I think we should stop dwelling on this question and start going through assignment questions of this assignment.
Chapter 5. We in chapter 5 and then so it said no harmonic oscillator.
Because he was like, because
Okay, maybe he meant quantum because you guys did like the Schrodinger method and whatever to get like the eigenstates of the harmonic oscillator, right?
yeah,
In the problems for chapter 5, like we did the exact
like
midterm question when we did chapter 5, and he said it stopped at chapter 4.
Wow. Okay.
Don't really want them to get taken off on returns.
Well, don't speak up. Don't speak up about it then. All right. So question like the penultimate question on the midterm. Is that what you want? Okay. Literally, you don't need any sort of. All right. Wait. This. Yeah.
Yeah.
Okay. I don't know why Pat decided. Just remove this.
I don't know, like how do we
Okay.
position for the energy?
So X is. I just need a quick look at it. Yeah, all right. So X of t, your first X of t in part A. A cosine omega of t. All right.
So,
So you
and you can prove that just plain x of
He
t.
didn't define x of t, right? He just said x of t.
well like a generic X. You're supposed to know, but like I was like. And then I thought like what the hell is X of t? And it's like, oh, the students should know this. I'm like, I can try and argue, but I'm not gonna win.
Find x of t is close to t because I did do the practice exercise.
Well, like x of t was supposed to be x of t plus t.
Yeah, that'll come in the proof. So
Because we never saw that up until problem set 4, the homework set.
okay, if Pat would have given you this, you would have, even if you didn't take quantum ever, you would be able to solve this problem. Show you how. Okay. So literally all this question is asking you is to prove or show the periodicity. And then from there you can get like the nu is equal to 2 pi over omega. Hold on. La 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 la. Yeah, omega over 2 pi. So no.
You just had to write how
Ah crap, hold on. Sorry. Yeah, omega over 2 pi. So basically the property of periodic functions is that we have x t is equal to x of t plus t. So big T is your period, right? So if you shift your sine function over one period, it'll become the exact same thing. That's what makes a periodic function periodic, right? All right. So you have your big T here. You also know that a cosine or a sine function for that matter goes through an entire optical cycle, or like it goes through an entire cycle over 2 pi radians. So you have x of 0 equal of 2x or x of, well, yeah, 2 pi whatever. So you have this right here. Okay, hold on. Yeah, all right. All right, so for the purposes of this problem, you can set like just your initial t equals to 0. So then if you have a plus t here, you have your period is equal, or no. Okay, yeah. So you have
You just need
cosine. This makes sense, right? So you just added just one period. This is your omega t. But then you have omega. But then you know also that you also know this, right? So you basically just set omega t is equal to 2 pi. So you have t is equal to 2 pi over omega. But then your frequency is 1 over your period, right? So you just convert it and you get equal to omega over pi. So if you show me this, you would get full marks. Or if you literally just did a statement like this and then did a bit of math, I would have given you full marks because it meant you understood enough of like why like sine functions are periodic or cosine functions are periodic. All right. So for the second part, all you had to say was that it's a linear combination of two trig functions with the same frequency. So the overall function has the same frequency. That's all you had to say. There are also a couple students who had a very interesting solution. I had to try it out for myself. Basically, what they did, I'm not sure why it works, but since it was creative, I gave them full marks. I'm not sure if any of you people are here, but they took they took a derivative of the a cosine omega t plus b sine omega t to pull out the frequency components, and then you can actually see that the overall frequency is omega because you pull out an omega in both, so you get an omega. That I'm not sure if that's like overkill, but it works. I tried it for myself and it works. And for example, if you had a 4 omega, so if your function was 4 omega cosine 4 omega t plus sine 2 omega t, well then your common divisor would be 2. So you'd have your frequency of 2 omega. So whatever, the math works out. So I give you guys full marks if you did that too. So is there anything that wasn't clear? Because I was a bit shaky on this explanation. Please let me know if I need to go over it again.
Sorry, T is equal to 1 over frequency, right?
Yes, 1 over mu. All right, are we all good? I can erase this. Is there any other pet peeves with the midterm? Any other like questions you'd like me to go over?
Besides the question 3, like the part 3 question 1. I think it's just like I don't know.
Yeah, the wording was
It's
pretty
like, I
bad.
don't like how we
Oh, very quickly, I'd like to do section 2, question 2, which is the photoelectric effect. So I literally debated this with Pat, and like there are many different like solutions. So there's a classic so the classic plot for photoelectric effect, you basically plot this. So you have frequency, and you have KE of your ejected photoelectrons. So you get something like this, right? So you have your work function here, and then you have like your threshold frequency. All right. But what happens if you have like two photons that absorb at the same time? So normally your kinetic energy is equal to h nu, so the energy of one photon, but then you have like cost from the fact that it has to leave the metal surface, so your work motions. It's this, all right? So if you dump instantaneously twice that amount of energy, the work function will effectively be halved. Like the threshold energy will be like divided by 2, right? So you have this. Oh crap. Oh no, I'm second guessing myself. This is bad. Okay, I'll get back to this one on the end. But basically, one of the big features that was different was that since you have two photons, you have twice the slope because you have KE is equal to h nu plus h nu. So if you put these together, you get twice the slope. If you decided to make, so here you have intensity. So basically the amount of light you're shining on your sample. So let's say you've already like gone past the threshold frequency. You have this. So your intensity, and then here is like your photocurrent. So for one photon absorption is like this, and then eventually like tapers off because you're probing the density of states. Doesn't matter. All you need to know that if you have two photon absorption, it's basically like a probability game. Basically, you have a probability of absorbing. So the probability of absorbing two photons is the probability of absorbing one photon squared. So that probability, so that fact makes it parabolic, like this. So you have two types of plot. Some people mix and matched and got part marks. Some people got most of the way and got most of their marks, but some people, I think, yeah, like one. Yeah, I'm pretty sure. Yeah, there were a couple people who like nailed either one of them. Yeah, but one of the things I saw a lot, there's no threshold energy here. Because if you get photocurrent, well, that automatically means that you cross the threshold energy. So there's no like energy threshold here since it's light intensity at a fixed wavelength. All right. Now, do you guys want to go over assignment question? You guys want to do that?
Yeah.
Yeah. Is there, well, have you guys submitted yet or no? All right. Is there one problem that's, you can do one or two problems. I'm not going to do all of them because you have. Okay, which one is that? I did go over these. So chapter 6, right?
Wait, you're not.
36. Oh yeah, that's an annoying problem. Okay, so basically, okay, so they say show that the first few spherical harmonics in table 6.5.
I don't want to interrupt, but I reserve the room to do analysis for all of those on the computer. Do you guys mind if I just use it?
Yeah, go ahead. Yeah, we don't mind. All right, so the problem asks you to compute the orthonormality of the spherical harmonics, basically just for orbitals. So hold up, there's a few things to unpack.
I just asked what they were in. Did they say like check the first few? How many is a few? Like
Okay, so here they say, so we have 1, 2 in the solution set, 1, 2, and hold up. Yeah, give me a moment. I actually have to find that table in the textbook. I have it right here. Textbooks.
I know like a proper like review for.
For sure. Yeah, I might actually do like 2 of them because yeah, yeah. Yeah. Yeah, actually, I'm not sure because yeah, he did publish like previous midterms, right?
Now we do.
Now he did for some reason. I don't know. I asked him like, hey, I have access to like the old midterms. Do you want me to publish those? And he didn't answer me. So
But do you think that like the final will be closer, like
The material.
Linda's? Because like Linda's midterms and finals will probably not cover the same.
I don't think.
If
you're absolutely right. That's what I'm worried about.
Right?
Yeah, hydrogen atom, right? You're not.
No.
If you're doing multi-atom stuff, you're not going to do any math. You're going to look at it qualitatively.
Sorry.
If you're looking like you guys did the hydrogen atom, right?
Yeah, we're jumping.
Like you did, yeah, all right. You went through it, whatever.
I have to go through the hydrogen atom this weekend on the textbook and maybe other separate stuff.
Okay. But then, yeah, then there's a problem of like the multiple atoms. Yeah, you haven't started yet, but it won't. I kind of forgot the question I was trying to answer. The multi-atom stuff.
Are we gonna finish the content before the final? Is the content gonna be?
I really hope so. I don't know if I can answer that question. Because I don't know, not because I don't want to answer.
I know.
All right. So they're asking for. So there's back to the problem. There's table of spherical harmonics. Where is it? 657. Aha. Absolutely. Do not. The fact that I had to look them up in the textbook because I don't remember them tells you all you need to know that you don't have to remember. Don't remember the Hermite polynomials either. Those will be given to you. Though I doubt he would make you suffer through Schrodinger's method again for the harmonic oscillator. All right. So they basically say.
Is he gonna still let us have a cheat sheet? Because that's what he told some of us.
You said that there'd be a cheat sheet on the final?
Well, Nicholas talked to him and said that he said we might be able to write our own. But again, I have no idea.
Yeah, I hope so. I mean, there's pros and cons to both.
Well, the cheat sheet he gave us for the exam was useless. It didn't even have
The signed
the integral we needed, which was the sine squared.
Oh wow.
So it wasn't really helpful at all. So
It had like a billion other identities.
Oh wait, the sine squared for section 3 problem 1. You didn't need to do a sine squared. Wait, the sine?
Yeah, because we're doing that over.
Oh wait. No, you do the integral first, then you compute the square, I think. Hold on, let me see if I have to eat my words or not. Yeah, you compute the integral. Yeah, you do the square at the very, very end. So you didn't need to, but I still I still think that the sine square integral is something you should have. Yeah, it's something really important. Honestly, if Pat gives you the option for both, like having his equation sheet for stuff, like it might have things you might not have. Whatever, you get the idea. And having your own, having both, I think would be fair, honestly. All right, back to the problem. So you have to look at the normalization condition for the spherical harmonic. So you want to be able to know that like the spherical harmonics are like all orthogonal to each other, like amongst each other. So you start with the first one. So what they say here is the orthonormality relation is this. So you basically do a spherical integral over over the azimuth angle and the elevation angle. So I of theta, and then you do, and it's 0 to 2 pi. 2 pi of, might have to rotate the screen real quick. Yeah, here we go. So you have like basically, so your y. Then second spherical harmonic.
How do we pick the second?
So basically you have your first spherical harmonic. So first you start by comparing them with themselves. So for the first one, like these two will be the same. But then after the problem says, okay, now check like in between, like what, like check for like L equals 0 with L equals 1. Basically all this problem does is like, oh, you have to like just compute integrals. Like I guess the hard like conceptual part is just setting it up. But then after that, it's just computing integrals. So actually, I'll do like the first couple, and then I think guys can do the rest. If like you'll be able to set up the problem, and if you don't want to compute the integral, just chuck it into Simbo Lab or something.
How many do you want us to do?
Okay. The textbook does so. So let me finish writing this. Or oops. All
That was bad, this slide.
okay, yeah, this is good. Yeah, all right. And then this is like a direct delta function, but it should be equal to 1 for all of them, I think. Yes. So first you start with, so for the first one you compute is for like y's m equals 0, j equals 0. But then you compute it with yourself, and then they do it with, yeah, I think the asking is a bit too much. So you do it with this one first, and then so they basically compare this one with itself, this one with itself, this one for itself. They should all be like, they should all be orthonormal. All right. And then, oh, right. Okay. And then they basically they compute the overlap between this and this, this and this, and then this and this.
But there is no y 0 1. there's only y, there's no y10, there's only y0.
Let's see. Uh. Did I screw this up? What? Oh man, I don't remember this part.
We could probably-
Yeah, I need a moment. All right. And then they basically tell you. Okay, for some, I don't know if it's typo or something, but they start with the one, you're asking about the 1, this one? Or yeah, this is a typo. Ah, crap. Yeah, that should be 1. So they ask you to compute the integral, like over this. So these, like, if you overlap this with itself and they're both normalized, well, then it should be equal to 1, right? That makes sense. But then they ask, okay, now what if you compute the overlap between this one and this one, or this one and this one? Well, then they should be perfectly orthonormal to each other. So this relation should be equal to 0. So we're going to do the first one, we're going to compute the overlap of this one with itself. Though I think that's a bit too easy. So we'll do this one. We'll do this one. So you start integral 0. So you have the integral in here. And that okay, so they have so we know that y10 is equal to, let's look at the table. So over 4 pi 1/3 cosine theta. All right. So then, okay, what are they doing here? So set up the problem is see how line. And then, basically this square, so of cosine theta, I might have to erase this. Yeah, so basically just this squared and then and this, so and then azimuth angle you have to integrate over as well. So here, so yeah, you can just rearrange. You can put this on its own, like the azimuth angle, the phi angle. Since this doesn't depend on the phi angle, well, then you can just like place it separately here. So that's just equal to 2 pi. So this is just 2 pi, right? Since you're integrating over an entire circle. And then this thing doesn't look like as much fun. Okay, yeah, they skip a whole bunch of steps here. So
I think we just do these substitution.
yeah,
Do you want us to show the whole integration step? Like, are you okay if we just go from the integral to the?
yeah, just set up the problem and then you can just show steps, but don't skip through all the steps, but you can skip through some.
Cause like for the, like the, this is 1/2, so the overlap integral of like y11,
Yeah.
like, do you want, like, could you go through it? Because like, I'm getting 0, but I'm pretty sure you're supposed to get 1.
Yeah, you're supposed to get 1. You can try and go through it. You can put your attempt whatever on the problem, but then you can just go through with like use Mathematica or use like Symbol Lab.
Okay.
Like I think it's fair game. Like Pat literally told me, like when I took his advanced quantum, there were some like particularly nasty integrals. And Pat said use Mathematica if it's too much of an issue. So I think I'll say the same thing and say, hey, Symbol Lab is fair game. Because that kind of nasty like calculus is probably only reserved for problem sets. Because you have like more resources. But not as nice if that's on like an exam or something. All right. So yeah, that makes more sense. So we can start by, yeah, so this is being squared. We can just pull this thing out. So you have so you have 3. That's better. 3/4 pi. All right, and you can already solve this thing here, which is 2 pi. And then you have your integral. So cosine squared theta sine theta. I have no idea how to compute this. I mean, I have the solution manual right now that does this, but let's actually see what Symbol Lab has to say.
Cosine u and then derivative is negative sign and then you can just replace it.
Yeah. Are you're taking Cal 3 right now? No, okay, come on, how do you guys remember this? So it's a use I forget how to do these things, man.
To say u equals cosine of theta.
Okay, so you
That's the only thing I knew how to do.
it's a minus sign. Theta.
D theta.
So yeah,
So your integral is
yeah,
just
the
u squared
is
minus
oh
u
wait.
squared. No, that's good. That's right.
Oh, before?
Yeah.
that- And then your signs cancel out, so you end up with minus squared.
Yeah, I'm having skill issues right now, sorry.
Oh, my goodness.
All right. Can you do it?
It's just minus u squared du.
Minus u squared du.
So then the integral
That's
is
it.
minus u to the power 3/3, and then you can replace u back by the cosine, and then you just calculate.
Minus. So this is equal to this, and then you just sub in, so it's minus cosine cubed. So okay, yeah, minus. Oh god. Over 3, which is yeah, that's it. Oh, but it's over 0 to 0 to pi. So that's just a 0. A sine of pi 0. Wait, what? Oh, so if you evaluate this from 0 to pi, you have So it's minus one over 3. Yeah, cosine of pi is -1, but it's minus that, so 1 over 3. And then you do minus, and then this sign. So that's 1, but it's -1, so it's plus 1 over 3. So it's equal to 2 over. I'm gonna move to this part of the board. It's easier to work with. So you have 2 over 3 times 3 over 4 pi. So this. Oh, and this is just 4 pi over 4 pi. So it's just equal to 1. All right. So yeah, you can do U subs, or you can use Symbol Lab. I think I've been using Symbol Lab as a crutch for too long, which is why this was an issue for me. All right. But yeah, the rest is pretty much the same. Actually, I'll just do a my courses assignment, my courses like announcement saying like, okay, do this part. If you do part, yeah, I'll just make an announcement, just like to correction, or just edit like the assignment details. I'll just edit that. But again, this is like a very last minute like change. So if you just go through like part of it, like you probably get the idea once you do like two of each, like 2 of like overlapping with itself and 2 overlapping with another spherical harmonic. Yeah. Is there another problem? Yes.
Question 43, the transition between the 0 to 1.
Oh, la 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 la.
Yeah, like, sorry.
Order. Oh, what is that? Hold on. I didn't see this one. I'm gonna have to read through it. Okay. Calculate the ratio of the dipole transition moments for the 0 to 1 and 1 to 2 rotational transitions in the rigid rotor approximation. Okay. Oh boy. First, let me erase this. You guys are good with this, I think.
Oh. Yes, that's true.
I want to go through like the entire problem and try to understand it so I don't like run into like surprises while I'm doing it with you guys. All right, let me actually find in the textbook where they give you this dipole moment transition probability.
I know.
Just give me like 3 minutes and I'll be good. So you have this. So you have m equals 0 for some reason.
What does it mean to you?
Oh, come on. Where is it? There it is. Okay.
What's something?
Okay, so let's do this. All right, so you start. So it basically wants a ratio. So it wants basically just a ratio of like two overlaps. So we have so if you go in the textbook, it shows you that you can compute. So if you go on page 290 of the textbook, you see that you can actually get like an overlap integral for the transition moment dipole, or no? Yeah. So well, from 0 to 5 of and then you're so this one is over phi, this one's over theta of so you have y of I, and then you have y. And then they have cosine theta, sine d theta, d phi. Okay, so you have this huge thing. They want you to compute that. So this is for the first transition. Oh, that's neat. I think they give you in one of the examples the solution to this integral. So do you guys want to do you guys have a PDF of the textbook on hand? Yes, okay. So do you go to page 290 actually? Because they do go over this problem.
Oh, it's example 6-9.
Yeah, that's it. So they do compute this integral. So I'm not sure why that is, but they say, okay, they want the integral over phi to be non-zero, because if your integral is 0, well, then that's pretty bad. You get like a 0 and put that in a ratio and you get like, yeah, it's not a desirable result. So you set m equals to 0, so your magnetic moment to 0. So you just have, so yeah, for that function, so this integral is of I have to go back to this stupid table. Oh, okay, here we go. So we can so for the first spherical harmonic, your 0, 0 spherical harmonic, you can just pull it out since it has no dependence on any angle. So here. And then you have your second one, which is 0, 1, which is 3. Oh, I should move this here. So 3/4 pi. 4 pi. Then you have a cosine of theta in there, but you can just let this, so you have a cosine squared, not this thing again. Alright. So if you do the first integral, yeah, you can do this.
That was 2/3.
Sorry? Yeah, it was 2/3. Yeah. Yeah, we can skip. So whoops, that looks awful. And then you have your 2 pi from integrating 0 to 2 pi for the pi. 2/3. All right, so let's bring it all together. So that's 4 times 3, 12 divided by 12 pi. And then is, which is 2/3. Yeah, 3/2. Times 3, which is 2 over pi. 3/2.
I think you forgot a 4 pi now.
Oh, I did 4 pi. Wait, here?
In your simplified.
Because I did 4 pi times 3/2. Basically, I just like put these two together.
But it already canceled out.
Oh yeah, why did I do that? Well, I mean, yeah. It does go. I don't know why I do that. Why I did that. I went the long way. But yeah, did you wait, yeah, hold on, something's wrong here. Let me just look at what they get. Okay, what? Wait, what? Okay, I'm not sure if there's a typo somewhere. What the hell? Just a moment. Oh, that's why. Forgot this one here. Yeah, thank you. Oh, hey, Alex. Yeah, everything's good.
No, you got a second?
Oh, yeah, yeah, real quick. Oh, yeah, okay. Actually, I'm in the middle of it. Yeah, I'm in the middle of a tutorial, so
Sorry.
don't worry. Yeah. Uh, okay, so this is just. Just four eyes.
That poor time has a.
Okay, I don't know. I give up. I'm just gonna go with what the textbook gives me, which is for some. Whoa, whoa, whoa! What did they do here? Okay, it's just so 1/√3. Okay, yeah, this is also what you get for example 6-9. Is it? Yes, it is. Okay. So then you have to do the same thing for the 1 to 2 transition. So you have the second integral. Let's just keep this part in mind. I'm just gonna erase it. Too much space. So this integral is from I. So you have your two spherical harmonics, and then it says here, so the magnetic numbers should have to be equal to each other for the integration over phi to be non-zero. So let's just see here. Okay, and yeah, they basically say just pick m equals 0 because that's the easiest thing to do. So let's look at our table here. Oh boy, yeah, it gets kind of ugly. So we'll pick the y02 spherical harmonic, which is this. 1/16 over 2. And then you have your y01. And you have, so I'll put in the cosine theta for the first spherical harmonic. And then what about y02? So this is 3 times cosine minus 1. And then you get the rest of it. Hold on. And then you have another cosine theta, sine theta. No. All right, yeah, so you get this monstrosity. All right, and basically they just distribute the terms. Yeah, we're not going to solve this. Wait, is it? Yeah, I think you could do a U sub. Maybe. I'm not sure. If you chuck that into Symbol Lab right away, I would have no problem against that. But yeah, basically the answer to this roll we're not gonna do is 15. So you get a ratio. So your ratio on your transition moment dipole. 1 over number in which is equal to square root of, is this right? Oh, something's not right. Yeah, 2. You're right. Which is 2 great. Oh no. 1/2. Okay. So it's basically over 2. So that's your probability. Sorry that took that long. All right.
I have a question for I0 to 2. Is it 0 to 2 or 1 to 2?
1 to 2. Thanks for spotting that.
I don't have any more questions.
Yeah.
Although, like, just does anyone actually understand what's going on in class at the moment?
Okay. What are you guys learning?
I have no idea. Like, actually,
Let me look at your notes and try and like construct an image what you're learning. Because are there any written notes on this?
we've got like some kind of like perturbation theory.
Oh man, that's mean.
Doing matrices and the
Yeah.
quantum
Yeah,
numbers.
just don't say
Very well.
Can you just tell him
There's so many
that
steps.
it really does not make any sense at all, and
At all.
telling us to come to class does not solve the problem because his class doesn't make sense.
Yeah.
Okay.
It's not even sentences.
What I can ask him to do is for him to give me a condensed lecture, and then for me to make a pre-recorded lecture of that.
That
To
would
show
be,
you
that
the
would be
data.
helpful.
really great.
I could try and do that because I don't know what material he's following exactly.
He's not
Take
following
my
the
notes
course.
if you would like.
It's
Like,
just
they're
not.
Okay, Zeeman effect, that is pretty important.
Like it's impossible to. I don't have like a sense of where we are or what we're doing, so I just can't follow anything. And it feels like going to class is like a waste. Of
Okay,
time.
when
I
did
can't-
this begin?
None of this makes sense.
After the midterm.
After the midterm,
Like,
so
what-
that's the 27. Oh
Harmonic
boy.
oscillators when he really started, I think, to lose people, and that's when people stopped doing class.
Yeah.
Also because.
Wait, how many did you lose?
How many
Over
people?
half the class.
It's like there's like
There was
there's
one
like
lecture-
10 people.
There was one
like
class where
7
we were 8
people.
students.
Like no one's
No.
going.
And
because
he
it's
doesn't
just-
follow the course,
because
so
everyone
we're
thinks
Half
it's
of
a
us read
waste
the
of time
textbook
to go
and
to
that made
class.
sense. And now it's
Now
not in the
he's not
textbook
doing it. Yeah.
anymore, so there's no way to understand.
once he started rigid rotators, I feel like anyone who was following at all got completely lost.
Yeah, like I just have no idea. Like the first part of the class didn't make sense either, but because you had the textbook.
You
it
can
was
lean
both
on
the
that.
textbook,
Yeah.
You could then kind of pick
like,
up on like
scrape your
what
way in.
vaguely was happening with the textbook.
All right.
But now it doesn't make any sense at all, and it feels like
Well,
like,
the
you
whole
mentioned
class is-
Levine.
the whole class is freaking out
does-
because no one knows how to study
He
for the
keeps
final.
saying some of the
basically.
materials in Levine or like.
Okay, well, let's look at
He doesn't
Levine
say where
together.
But then he said
Uh,
last class, he said that he like takes it from a bunch of different textbooks
Yeah.
and he can't like recommend one source.
And he doesn't
So he
remember
asked
when
for
he
sources
learned
and
it.
doesn't really give us one.
The source is that he made it up. All
Yeah,
right,
exactly.
whatever.
Like it's
That is problematic. He probably
Like I would not.
okay. Does he have a stack of paper that he reads from?
Wait, after classes because it forces people to come, but he still hasn't posted them. It's been since after the midterm that I asked him.
Okay, let me do that. Maybe digitizing them in LaTeX would take way too long. Yeah, I can scan that. Well,
And he's not explaining anything. and he expects us to understand all of this when we don't. Like
It's
he just
so many
he does
steps.
he thinks we're like I feel like he's in the brain space if he's been teaching advanced quantum, so he expects everyone to be able to pick this stuff up and be really interested in it. But
Yeah.
most of the class doesn't even want to be in this class.
Yeah, that's the distinction. Like the
You are
people
not-
taking advanced quantum want to be there.
But it's not
Literally.
it's like sentences, like he just dictates the equations he writes on the board. So I can write down the equations, but I don't.
But then you have
And meanwhile, he's writing, he's saying.
okay,
something like-
I get the idea. I get the idea. I think
Like the majority of us have taken 2, maybe 3 university physics courses. Like this is like we do not know what's going on.
God, I wish Linda were here.
Yeah.
Yeah.
Would be helpful.
He just needs to
Like,
really
maybe
dumb
say,
down
this equation means this.
and maybe review some.
Write things.
All right.
Not just like.
Well, I saw him earlier, so I think I should go talk to him.
That would be great.
Okay, I'll try to get something. I'll try to get like something like concrete that'll like help you guys.
Even like if there's like a quantum professor like on YouTube or something that we can
Yeah.
watch their lectures that
I mean, there's a lot of stuff on YouTube. I can make like I could also make like a My Courses announcement, like
Yeah, just-
a whole mess of like YouTube resources.
Yeah.
Yeah. Yeah. Maybe stuff that'll help you more. Are there like, is it more like the like core topics? Because like if you really want to like understand like what a wave function, like a real wave function actually looks like, or like, oh, the math.
But whenever he starts doing equations, he skips so many steps.
And then he doesn't tell you
And
when
then-
he's skipping. So then you're just
Yeah.
like, where did this come from?
And he often like does substitutions. Variables that you don't.
Yeah.
yeah, I'll just be like, oh well, I just put in this new variable A. I'm like, what is A? What does it mean? And he's like, I don't know. Like,
It's
you'll
just
find out later.
Okay. All right.
Look at
And make him. I know Pat may or may not like this, but like literally make him stop. Like, and he doesn't. It doesn't help. Oh God. All right. I think.
Asked a question like to clarify, he'd be like, review your notes later and then come back and
Yeah.
the question.